Hello everyone, my name is Victor, and today I'll be introducing you to my research into improving Northrop Grumman's GEM 63XL solid rocket booster. The primary goal of the research was to gain an increase in maximum thrust, which was obtained, but many other parameters were also achieved and surpassed in the process to increase maximum thrust. I will go over the four propellants that I came up with, as well as a breakdown of their performance. One thing to note about this research, though, is that it was entirely theoretical, using many ideal rocket performance equations that might not hold up as well in the real world. So much of the data in this research needs to be experimentally verified and tested. First, I'll go over an introduction into my research and what I'll be doing. My focus for this research was improving Northrop Grumman's GEM 63XL, which can be seen in this image in the corner here, while keeping the same overall dimensions of the motor. This means that the motor's height and width will be the same as the dimensions given by Northrop Grumman. However, I will be changing the propellant mixture, the propellant's cross-sectional geometry, how the propellant is distributed along the length of the booster, and the nozzle that is equipped onto the rocket. Through this, I will give four novel and different propellant mixtures, one new cross-sectional geometry, a new equation to describe the propellant distribution, and a new nozzle geometry. For the nozzle geometry, I'll be giving the area of the exit and throat. All four of the propellants in the study gain an increase in maximum thrust compared to the maximum thrust reported by Northrop Grumman. In addition, I also analyzed the effects of nozzle regression, since at the extreme temperatures which are required for sufficient combustion and ejection of mass, it can very easily wear down the nozzle and expand the throat area. This would decrease the effect of the nozzle and make the craft slightly less optimal. In addition, I also did calculations of ideal and applied performance. Ideal performance assumes no nozzle regression and would represent basically a ballistic test, with just measurements of thrust versus time. This represents the theoretical maximum possible performance outputted by each of the propellants. The applied performance, on the other hand, has nozzle regression and simulates the motor like it was a booster on a mission to bring a payload of 5,500 kilograms into low Earth orbit. However, as mentioned previously, the actual performance may be overestimated since this is taking place in a simulation and has not yet been experimentally validated. Before I get to the results of my study, I want to quickly go over what the implications and larger purpose of my research is. As most of you have seen in recent events, space exploration and building more powerful rockets has been a hot subject. While the developments spearheaded by private companies like SpaceX and Blue Origin are recent, the idea that space exploration has always existed, and it is the next frontier of humankind. Space exploration is important for scientific research, exploration, and setting humanity up to inhabit other planets like Moon or Mars. Currently, the best method of getting to space is with rockets. Whether by using liquid, solid, hybrid, or electric motors, rockets are the most dominant form of space transport. Solid rocket motors, in particular, play a key role as boosters for various rockets, as it allows them to start with a good amount of initial thrust and altitude. For example, the SLS, which is seen in the image in the upper right corner, or the Space Launch System, is a rocket developed by NASA for the Artemis program, and it uses solid rockets as boosters. In addition to that, many of Japan's rockets are using solid rocket boosters to help bring their satellites and other payloads to space. Since solid rockets are still very useful in the current aerospace industry and is relatively easy to make, the main problem with solid rockets is getting more powerful propellant design and mixtures. This is achieved by modifying the composition or its distribution in the rocket motor. There are many different compounds that can be used as propellants, so every combination of propellant mixture has not yet been discovered. This sets the stage for more powerful propellants to be discovered. This study, as a result, the study is going to focus on a theoretical approach to simulate performance with a Python script that incorporates various rocket equations to get a near approximation of the rocket's thrust over time. This Python script uses the NumPy library, Matplot library, and PyGasFlow library, which is used to calculate isentropic flow for exit pressure calculations. When moving on to my results, you can see the notable parameters gathered in how each propellant's performance. The table shows the propellant mixture, its max thrust, and its total impulse, as well as a percent comparison to the GEM 63XL's rocket. The most powerful propellant in this data table by thrust is propellant number 4, with a maximum thrust increase of 98%, which is nearly double of what GEM 63XL is able to achieve. When looking at all the propellants, they all have a higher max thrust and total impulse. The increase in total impulse is around 165% when looking at all of the propellants. When you're looking at the cross-section and propellant distribution, the cross-sectional geometry uses a star shape, as shown in the figure below the text, but with 2 points, so it looks like a diamond. The distribution follows a square root distribution, as shown in the figure below the table, so that instead of a linear distribution, so there is, on average, more propellant concentrated near the rear end of the nozzle. The throw area and the exit area for the nozzle would be 1 and 10 meters, 1 and 10 meters squared, respectively. And then when you're factoring in nozzle regression, it only has an effect of 2 to 3% on the maximum height of the applied performance. So it has a very minor effect on the overall performance of the rocket. One thing to note on why propellant number 4 and propellant number 2 are higher performing than the other propellants is due to their composition. AP, or ammonium perchlorate, is often used as an oxidizer, aluminum powder is often used as fuel, HTPB is used as a binder, and ferric oxide, or FeO, and lead stearate, or PbST, are used as catalysts for the reaction. With high amounts of catalysts and low binders, these propellants provide a more powerful and energetic kick than the rest of the propellants. These graphs show the ideal performance and the applied performance of the propellants. The ideal performance graph has only the thrust performance because it is simulating a ballistic motor test with no payload and is purely measuring the thrust output, thus giving the theoretical maximum performance of the propellants. As a result, the applied performance graph will have a lower thrust because it is not in an ideal scenario and has to deal with the effects of nozzle regression. One thing to note is how propellant number 3 actually gets the highest height out of all 4 propellants due to its long burn time. Even though it has the lowest thrust performance, it has a long burn time that can keep it burning seconds after the other propellants have burned out completely, thus allowing it to get a higher altitude before running out of propellant. The propellants in the ideal performance follow a curve where it peaks around 10 seconds and then it drops down at 50 to 60 seconds before leveling out because of how the propellant is arranged in the motor. Since it follows a square root distribution where most of the propellant is not at the end of the nozzle, it can get a peak burn relatively quickly before dropping significantly as propellant is consumed before leveling off at a steady rate. In the applied performance, we can see that where it would level off, the propellant performance actually shoots up quite a bit because the thrust equation has a term that is the difference between the pressure at the exit and atmospheric pressure. And this difference is amplified as the propellant travels higher because the atmospheric pressure is decreasing, thus increasing thrust. Overall, this research has delivered theoretical models of simulated performance. Again, it will need experimental testing to verify the performance values due to many assumptions and limitations that were taken in the code to speed up processing power and simplify the calculations. Regardless, the 4 propellants analyzed house many potential improvements to future propellants and have possibilities for breakthroughs in discovering even more efficient solid rocket propellants. This is an essential step in helping rockets transport heavier payloads into space, which can aid humanity on its mission to become an interplanetary species. If you're interested in looking at my code to get a more in-depth look at my research, you can find it on GitHub by going to that link on the slide. And if you have any questions about my research, you can email me at vyang0607@gmail.com. Well, that's all I have for you. So thank you so much for listening to my presentation on my research.